What we're going to be doing next is to try to find the most parsimonious model possible that best estimates the response variable. In other words, we want the model that's the smallest possible, meaning also, let's say, the smallest number of explanatory variables, but still gives us a very, very good estimate of our response variable. Also, what we're going to be doing next is looking at how we can assess the fit of a model. In other words, we might want to find out if there are some observations that are not estimated well by a corresponding model. Also, we might want to try to find some observations that, let's say, really influence the model fit. That would, if the particular observation wasn't already in the model, the model would change. And so that's the purpose of this particular chapter, is to look for the most parsimonious model possible that best estimates the response, and also to assess the fit of the model. Now, if you've had a full course on normal linear regression analysis, you're going to see a lot of similarities to what you did in that particular course. If you haven't had that particular course, that's completely fine. I will assume that you have not. Okay, so to begin here, we want to talk about, well, which variables, which explanatory variables, should we include in our model? Now, in some situations, you don't really have a choice. So let's say maybe you have some kind of designed experiment. Let me get my red pen going here. You have some kind of designed experiment, maybe with 3 variables. In that particular case, you would most likely want to include all 3 variables in your model, because you have this design experiment where maybe you're controlling all the other factors that are out there, and you're very, very interested in those particular 3 variables. So in that particular situation, variable selection isn't of interest. Now, another situation you might be involved with is that, based upon your knowledge of a particular subject, you might always want to include a particular variable, maybe a particular interaction in a model. In that particular case, you're not doing any kind of variable selection because you're always going to be including that. Now, in this last situation here is basically what we're going to be focused on in this part of the notes. Suppose you have a lot of explanatory variables of interest, like with the place-kicking data set, and you really don't know, well, which variable should be in the model. And in that particular situation, we would like to have some kind of tools available to us to make the decision. Should this variable be in the model, or should it not be in the model? Now, to help then make that decision, we're going to look at a tool called information criteria. To help motivate this, let's think about how we might want to approach this problem without necessarily thinking about information criteria. So let's say we have 2 models of interest. Maybe one model has x1 and x2 in it. Another model has x1, x2, and x3 in it. One approach then in this particular situation to evaluate which model is, let's say, best, in other words, should you have x3 in the model, is to do a likelihood ratio test. That's a standard approach. The key, though, is that these models need to be nested. In other words, everything that's in this model has to be also in that model. Think of a null hypothesis, alternative hypothesis model. So obviously there might be models that we want to compare that are not nested. So what can we do? Well, you might be thinking about, how about we just look at the residual deviance for every single model? Because we know that the smaller this residual deviance is, the closer the model is to having, let's say, a perfect fit to our data. Alternatively, maybe just look at the likelihood function itself. Going back to what we originally were talking about with likelihood functions, the larger the likelihood function, the more plausible the set of parameters are, or parameter values are, for a particular situation, or in other words, for a particular data set. Of course, in our regression setting, each of those parameters are associated with a particular explanatory variable. And so, in other words, you might be thinking, okay, the larger the likelihood function is, then the better or more plausible a particular model is. Now, that's a logical approach, but there's a problem with doing that. And that is, as you continue to add variables to your model, even if these variables are not really meaningful at all, the likelihood function will always go up. At least a little bit. It will always go up. And so, in the end, there's basically no bound in terms of, well, if you have an unlimited number of variables, you're going to have unlimited size to your model, and that obviously is a problem. And this was the problem for why R squared itself in normal linear regression analysis is not a good tool to use in this kind of a variable selection process. That's why you learned about, for example, an adjusted R squared if you've had one of those, had a course on normal linear regression analysis. So what we're going to be doing with our models is use an information criteria to help choose between the models. Simply, the lower the value, the better the model. Again, the lower the value, the better the model. Now, to see how this information criteria work, we're going to look at it in terms of the likelihood function. And remember what we were talking about before, the larger the likelihood function, the more plausible a set of parameter values are. In other words, the more plausible a particular model is. And so what the information criteria does, it's false. First of all, we simply abbreviate information criteria by AIC. And notice it's going to be a function of something that we're going to be talking about very shortly here. We're just going to call it K for now. And so what we're going to do is we're going to take -2 log my likelihood function evaluated at the parameter estimates corresponding to a particular model. Now, think about what this means. Again, the larger the likelihood function, the more plausible then the corresponding model is. If I were to take the log of that likelihood function, again, the larger the likelihood function, the more plausible that model is. But now if I take -2 times that log likelihood function, now instead of the larger, it's actually the smaller the likelihood function is. The smaller the -2 log likelihood function is, the better the model. We still, though, have this problem, though, as we add variables to our model, this -2 log likelihood function is going to continue going down, 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 down. So to counteract that, we're going to add a penalty. The penalty is simply K times R, where R is the number of explanatory variables, or it might be better to think of it as the total number of parameters, the total number of parameters that we're trying to estimate for a particular model. And so K then tells us how much this I guess you could call K the penalty itself, and we multiply it by R. And so notice as I keep on adding more variables to the model, and K is always going to be positive. Notice as I keep on adding more variables to the model, then this term is going to go up. And so as I start adding, maybe you could say nonsense variables, explanatory variables to the model, then this overall value here is not going to keep on going down, down, down. Instead, it can go up now because of that penalty. So once again, how does this work? A model that has the smallest information criteria value is going to correspond to the best model. Again, smaller, the better the model. Why? Because we work with a likelihood function here. We are multiplying it essentially by a negative, and then we have this penalty with it as well, where we take K times R and we add it to that log likelihood function. Okay, so what do we use for K? Well, we could put 2 in there, and that corresponds to something called AIC's information criteria. Sometimes this is pronounced as AIC instead of AIC. Most people will pronounce it AIC. And simply, wherever you see K in here, you just simply replace it with a 2. Then there's something called a corrected AIC, which is very, very similar to just the regular AIC for AIC's information criteria. Note that we put a C in the subscript there to be corrected. Again, it's very similar to just the regular AIC. But look what happens when n is large relative to r. R is the number of parameters. What's going to happen is that this part here is not going to play much of a role, and I have 2 over n divided by n, or approximately 2. So this corrected AIC is going to get very, very close to what the regular AIC is for a large sample size relative to the number of parameters that you're estimating for a particular model. When will then they be different? Well, when n is much closer to r. And lastly, there's something called the Bayesian information criteria, or the BIC for short. And instead of using 2 or some version of 2 there, we instead use the log of n. Now, where do these values of k come about? If you want details behind it and why we're actually using this information criteria, here are 2 references. In a PhD stat theory course, very typically you'll learn about something called the Kullback-Leibler information number, and that's what these information criteria basically are based on. So if you want to know more details about that, get a PhD in statistics. Otherwise, let's just use these measures. The lower the number, the better the corresponding model. So we've already talked about how these 2 different criteria are close to one another. Now, in terms of the BIC in comparison to the other ones, as long as you have a sample size that's not extremely small, the BIC, or this penalty here, this k, is going to be larger than 2. And so what that means then in terms of our value of what we have here, oops, let me get my eraser out, just a second. And so what that means then in terms of our value here is that I'm going to have a larger penalty. And so what that is going to do is going to penalize more for having more variables than if you were to use just the AIC or the corrected AIC itself. And so what ends up happening is that the BIC will end up concluding or suggesting that the best model is typically, let's say, smaller than what you would have for the AIC. They can be exactly the same, but we can see that we have a larger penalty to deal with. So let's see here. So we've already answered this question here. And so this then gets into this comment, and what I was just talking about. The AIC ends up favoring larger models. The BIC ends up favoring smaller models in terms of what is the best. And that corresponds to that penalty that we have here. The AIC typically will have a smaller penalty than the BIC. Now, what if, though, you have a particular situation of where you have, let's say, maybe 2 models that have an information criteria value that are very, very similar to one another, such as, let's say, 100 versus 100.000001. I think you get the idea. Which is the best model? Well, a strict application of these criteria, say the model that has just 100 will be the better model because it is lower. But we can see that they're very, very close there. And so you might be thinking, okay, well, maybe this model really isn't that much worse than the model with just 100. And so there are ways now to handle that kind of a situation. I'll briefly mention them later on in these notes. Now you might be wondering, why do we have to learn 3 different information criteria? Why can't we just use one? Well, the key is that, or my key point here is that one is not always better than the other. And so that's why typically one learns about these three. At the very least, typically everyone will always learn about the AIC and the BIC when one is talking about regression modeling, such as what we're talking about here. So how can we actually go ahead and calculate these values in R? Well, there happens to be a function in R called AIC that will essentially automatically do the calculation for us, where we specify what the K is using the K argument. Now, many functions in R also will automatically compute the AIC or the BIC or the corrected AIC for us, and we'll see those functions as we go along. Something that's very important to note is that while there are multiple functions in R that will calculate these information criteria values, for the exact same model, the different functions may come up with different values, even though you have exactly the same model. There isn't necessarily a problem with that. Why this comes about is that if you look at the actual likelihood function for a particular model, like a logistic regression model or a Poisson regression model, you're going to notice that there are terms in that model that do not change relative to if the parameter values change. And so because of that, some authors of these functions will leave off those constants that have no role at all. So for example, when one is dealing with Poisson regression, you have the corresponding likelihood function, you might log likelihood function, you might remember there was a term that looked like that, the sum of the log of the y factorials. That's not going to change for whatever variables you have in your model or what the parameter values are in your model. And so because of that, some authors of these functions might leave that term off. The key point that you need to understand is that then consistently use, let's say, one function to calculate all your information criteria rather than, let's say, use multiple functions to calculate the information criteria and then compare them. Just use one function at a time. Okay, so now we have a tool then that helps us decide, well, which model is better. In other words, helps us decide, well, which variables are better to include in the model. And so now we like to be able to say, well, which model overall? Let's say I have 3 explanatory variables. Which model overall should I use? And one approach then is to use what's called all subsets regression. And what that means is simply, let's say if I have x1, I have x2, and I have x3 as potential variables to include. Well, I could look at a particular model that only has x1 in it, not x2 and x3. I could look at a model that has x1 and x2 in it without x3, and so on. And so that essentially what we see here is that we have 2 choices for each of these variables. Is the variable going to be in the model, or is it not going to be in the model? And so how many different possible models would I end up having to look at? Well, 2 to the 3 factorial. And so we can see that here when I've actually written out all possible models. If I have then capital P explanatory variables overall to examine, that means I have 2 to the capital P different possible models to consider. The best model of these 2 to the P is the one that has the smallest information criteria value. So this is referred to as all subsets regression because essentially I'm looking at, let's say, all possible models and I'm looking at subsets of the corresponding variables. Now, in the end, we are not actually considering all possible models here. Because notice, at least what I've shown on the previous page, we're not dealing with interaction terms. We're not dealing with, let's say, maybe some kind of transformations of our explanatory variables. So we're not actually looking at all possible models, although essentially this is what the name of this procedure, how this name of this procedure comes about. And so in the end, though, what all subsets regression gives you is a way where you can, let's say, sift through particular explanatory variables of interest, come up with a particular model then to consider further. And what I mean by further, look at maybe possible changes on top of that model. And that's a lot of the stuff that we're going to be talking about in this particular chapter about how to do that aspect. Now also, as you can see, this 2 to the capital P, that value can grow large quite quickly as a function of capital P. Think about 2 to the 10, 2 to the 20, 2 to the 30. And eventually you get to a point where you just have too many variables, too many possible models to look at, and you're going to have computational problems. You're not going to be able to look at all the models. We will discuss shortly how to get around that. Now, to actually implement all subsets regression, there are no functions in the default. There are no main functions, let's say, in the default installation of R that will do this for you. And so we have to look at some user-contributed packages to get the tools to do it. And unfortunately, well, I shouldn't say unfortunately, I would say there are a number of good functions out there, but none of them do, let's say, exactly everything that I would want to do for this corresponding book. And so rather than us go through, let's say, all possible different functions and different packages, what we're going to do here in this set of notes is we're going to focus on one particular function from one particular package. In my corresponding program that you're going to see shortly, you'll see examples of how to use some of these other functions as well. And so we're going to focus on this package here. I guess I usually pronounce it MUM-in. Basically what this stands for is multi-model inference. And there's a function called dredge there. I'm not for sure exactly what the origin of the name is, but I would think it maybe has something to do with the fact that, when you're, let's say, dredging up something, you're searching for something. And what we're trying to do here is to search for, let's say, the best model under these constraints of what we refer to as models of interest. This package, this function works for up to 30 explanatory variables. So it works for a significant number of variables. So let's see how we can use this with the place-kicking data set. So first of all, well, how many variables do we have here? Is this function going to work for us? Well, we have our response variable good. And so how many variables? We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 different variables. That means that we need to look at 2 to the 8 different models, or 256 if you do the calculation quickly in your head. How do we then use dredge? Now, before we use it, we actually have to use the GLM function. We have to estimate a model that has all of our variables of interest in it. And so to do that, like many times we've done before, I say formula equal, there's my response, good, tilde, and this is where I can put my explanatory variables of interest. A little bit of a shortcut here is if I put a period there instead, that says, okay, let's take all the variables that are in the data frame, other than the one that I'm specifying for the response, let's take all those and use those as explanatory variables in my model. And so notice, I just want to emphasize this in case I didn't, notice I'm basically estimating, let's say, the largest, in terms of the number of variables, the largest possible model out there. Now, to get dredge to work, I also need to add the argument na.action equal na.fail. And what this just simply corresponds to is that, let's say I had some missing variable values. Dredge requires that you use a data frame that has completely everything observed, meaning you don't have any missing values. And so if I include that there, that basically will give us a warning that we have a problem, that we have missing values if they do exist. So I'm going to put the results then into an object called mod.fit, for the lack of a better name, specify my library or the package, and here's how I use dredge. So I say dredge my global.model, which is my largest model possible. I save the results in mod.fit, and then rank says, well, which information criteria do I want to look at? Let's look at the AIC here. Okay, I put the results into all sub.aic, and what that's going to simply contain is the models and the AIC values for all 256 models. What I like to be able to do is maybe look at the let's say the top 5. And so what I could do, this will actually give me the top 6. I could say head all sub.aic, or what one could do instead is in this object there's going to be a variable or a column in the data frame. Sorry, let me back up a second here. This is going to be a data frame that comes back to you. I should have said that at the beginning, where columns are going to correspond to the variables, but there's also going to be a few other columns, like a column that contains the AIC and a column that contains delta. And all that delta is, it measures the difference between the lowest AIC and the particular model of interest. So if I specify this syntax here, where that delta is less than 1, all I'm doing is I'm looking at all the models that are less than 1 unit away from the best model, the model that has the lowest AIC. Now, if we take a look at what's printed here in this model selection table, we see that we have our intercept, we have the change variable, distance, PAT, week, and when listed there. Here's the corresponding beta hats for that particular model. The 5 degrees of freedom then corresponds to them estimating 5 particular parameters. And if I page down here a little bit, we can see that here's the AIC, and the way that this particular printing function actually organizes everything is that it sorts it by the AIC. And so the first value, or the first model here, is the one with the smallest AIC. The second model corresponds to the second row, which ends up being model number 212 that I investigated. Notice it has now the same variables in it, but also week, and we can see its AIC is just a little bit higher there. What's the difference? 0.39 between the two. Now you might be wondering, wait a second, aren't we missing some variables here, such as field? Well, what ends up happening here in R is that when I print this out, R calls a print method function corresponding to the class that is produced by Dredge. It's called model.selection. And this print function will only print off the, let's say, the columns that we see here corresponding to the variables that would be, in this case, with a delta less than 1. Similarly, if I just simply had the top 6 actual models printed, this will only include those variables that include the top 6. Now, if instead I just simply printed all this here, you will see models that have a field in it. Okay, so let's take a look at the comments here. I think I've talked about it all. Again, model number 148, that's change, distance, PAT, and when, is the best model according to this AIC. But we do have some AIC values that are relatively close to one another. This in the end means there's a little bit, let's say, uncertainty about, well, which model is best. Now, what happens if there are a larger number of explanatory variables, more than 30, as what we saw here with this particular function allowed us to do? In that particular situation, you're not going to be able to look at all subsets of these variables. And so what you can do is use an algorithm that helps to search amongst all possible of these models to find what you would hope ends up being the best in terms of these information criteria. We're going to look at one particular algorithm called the genetic algorithm. Here's how it works. What the algorithm does, it first randomly, and that's a key word there, randomly selects. It should be selects explanatory, or I'm sorry, I guess I did get that right, excuse me. Random sets of explanatory variables are put together into models. So, maybe if I have, in a very simple case, let's say 5 variables, this algorithm will randomly say, okay, let's put x1 and x3 together. Let's also maybe put x4 and x3 together, and so on. And it estimates these models, comes up with the information criteria, and this is referred to as, let's say, the first generation of models. The models then are the best of this first generation are the ones with the smallest information criteria value. And from these best performing models, new models are formed by putting together in a random manner the variables from the first generation to form now a second generation of models. This process then continues, and along the way, for the generations, there are what are called mutations, meaning randomly maybe a variable will be taken out, or a variable will be put into a model. Think in terms of genetics, what mutation means. And so this process continues and continues and continues for many, many generations until eventually the algorithm converges. In our sense here, what that basically means is that for, let's say, a significant number of generations, there are no, let's say, changes in terms of what the best models are. Now that random there means that this is a stochastic algorithm, meaning that if I were to run it once and then to run it again, I might get perhaps a different answer in terms of what the overall best models are. So because of that, it's best to run this algorithm multiple times to see what happens, to see if you have much change. So that's the genetic algorithm. Now, at least right now, myself and my co-author, we can only find one particular package that can implement this. And this package is called GL Multi. And it has a particular function called GL Multi that implements the genetic algorithm and also does all subsets regression as well. Now, the reason why I was saying that this is the only package that we've been able to find that implements it, and the reason why I say this is because there are some drawbacks to using this package that I wish weren't there, and if I could find another package that works better, I would use it. Here's the first drawback. First of all, this package, or the function itself, I should say, uses a Java program that's built into the package to actually implement the genetic algorithm. To use this Java program, you need to have essentially the Java programming language on your computer. Now, at least many years ago, Java was on most computers. Nowadays, that's not necessarily true. So if you want to use the genetic algorithm, you're going to need to install Java. If you go to java.com, you'll find it. It's not that painful to install. And do note that there are different versions, like a 32-bit version, a 64-bit of Java. You need to install the version that corresponds to which version of R you're using, 32-bit or 64-bit. Now, at the time of making this video, R by default only comes in the 64-bit version. So this isn't typically as big of a deal. Everyone's going to use a 64-bit Java for a 64-bit R. But for those of you who maybe still have, let's say, an older version of R on your computer, take note about which version you're using, 32 or 64-bit, and install that corresponding version of Java. Something else that we don't like about this particular package is that the set.seed function does not work to set a seed with this particular function. Meaning that every time that I run this function, even if I say set.seed right before it, I could get potentially different results. I don't have a way to reproduce my results from one run to the next. I would imagine the reason why this occurs is because the random mechanism for the genetic algorithm is built into the Java program, and unfortunately the authors of this corresponding R function did not necessarily include a way that you could say, here's my seed so that I can always reproduce my results. So that's just what we'll have to live with if we want to use it. So let's go back to the place-kicking data set again. There are obviously a number of different arguments with GLM multi. Two that I want to point out here is there's an argument called method. And this basically says, is where you denote, do I want to use a genetic algorithm? If you do, put a G there. If I want to instead use all subsets regression, put an H there instead. H corresponds to the H in an exhaustive search, meaning you're going through all different models. That's where the H comes from. Also within this function, you can actually implement all subsets regression and also the genetic algorithm with interactions. So that's great. And what you need to do is if you want, let's say, two-way interaction, say level equal 2. The default will be level equal 1. And also when you do the interactions, it respects the principle of marginality, meaning that if x1 and x2, the interaction is in the model, the corresponding x1 and x2 are in the model as well, if you specify marginality equal true. Okay, so let's take a look at how we can run this code or implement this particular function. So I need to download the corresponding package and to install it, and then I say library GL multi. And then I'm going to put my results into this object here. Say GL multi. There's not a formula argument, so I say good. I say y equal good tilde, and I want all my variables my data set, so I put the period there again. My data is in place kick. I'm working with logistic regression models here, so my fit function corresponds to the model that I'm using to actually estimate the model. Let's look at interactions. Yes, respect principle of marginality. I want to use then the genetic algorithm. I'm going to use the AIC, and then I need to specify it's a logistic regression model. And so then what's going to happen is that after about every 10 generations, you're going to have an update printed about what is the best model. And eventually you get to a point where it converges, and you can use the print function to see what the results are. In this particular case, the smallest information criteria with a lot of numbers after the decimal place, the value for this is AIC 763.85 about, excuse me. And here's the best model. But oddly, in this particular case, there happens to be two models have exactly the same AIC value, and so this is the second model. The only difference is this term right there. This term is actually going to be very meaningful to us later on in this particular chapter, so stay tuned for that, and that will give you some justification for why this occurred. Okay. And so we have some other information here. I ran this on a slow computer, ended up taking 11 minutes total to do all the generations, a total of 730. There's some additional information here that's not useful for what we're going to be doing in this particular section. In a later section, depending upon if we end up doing it, I will go over what that corresponding information gives you. Okay, so in this particular case, since we included the pairwise interactions, we had 2 to the 36 different possible models that the genetic algorithm tried to search over to try to find what the best model was overall. Now, if we look back here, again, we're allowing for interactions. And notice we had a wind and distance interaction. That makes some sense to us based upon what we've seen previously in this course. We also have wind and field. That might make some sense because the way that well, I don't know if that would actually make sense now that I think about that. Why should it matter if it's grass or artificial turf for how wind affects the response? And so, sorry, I misspoke then about that originally. And so in this particular case, it helps us see something that you think that might be important from a practical standpoint, is that there may be some interactions that you don't want to investigate, like wind and field. Unfortunately, there isn't a way with this function to say, hey, ignore that corresponding interaction. And so that's another problem with using this particular function. Now, let's see here. Just a reminder, so the Y argument allows us to do what we normally do with a formula argument in GLM. Do note that the model that you specify there is not the only model that's actually being investigated. Simply what it should be is, let's say, your largest overall model, but if you're looking at interactions, you don't need to specify the interactions in there. Okay. So we can look at then, let's say, maybe the top 5 models overall. The way to pull the information out of the resulting object that comes about from this from GL multi is the function called weightable. And if I say head of weightable, I see the top. I have 5 there. I would have expected 6, but top 5 models here. With their corresponding AICs. And so we notice too in this particular case we have a situation where a lot of the AICs are very similar to one another. Now I did rerun this function a total of 4 times, and the 3 best models that I found in the 4 separate runs were all exactly the same. So that made me feel good that I'm not necessarily missing something through the random part of this variable selection process. Okay, so that concludes that example. There's one last thing I want to mention here. This corresponds to what I was alluding to before with respect to some of these AIC values being very similar. When you have that, this is a sign that maybe uncertainty exists about, well, which model overall is best. And while if we use a strict application of these information criteria, simply the model with the smallest is the best. However, there are alternative tools that you can use. In particular, instead of choosing, let's say, one overall best model, maybe what you could do is, let's say, choose a number of models that all, let's say, have similar AICs, and then simply, let's say, take the beta hats that you see for all those models and average them. That is what's called model averaging. Kind of an interesting technique. There is a section in chapter 5 of my book if you want to know more about that and how to use that technique. Okay, so that concludes then this introductory section to variable selection.